So we're going to be working on electronic spectroscopy and the selection rules. Electronic spectroscopy is the most difficult to understand, as you might imagine, because we're dealing with the most complex part of the molecule, the structure of the electron cloud. And we need molecular orbital theory to understand that. Local bond theory doesn't cut it because we don't have two electrons stuck between each atom in the molecule. We have this molecular orbital, which is the structure of the electron cloud, where the electrons are oscillating all around the whole thing in terms of waves. I'm focusing on inorganic compounds today to prepare you for advanced inorganic. And then we're going to make sure that you have the good take-home lesson of being able to do the selection rules. And that's the standard direct product table symmetry stuff that you're used to. So let's dive in. Whenever we have a transition metal, things on the 3D, 4D, or 5D unfilled subshells, and those are in complexes, we see splitting, this d-d splitting. They come in as 5 degenerate orbitals. There's no energy difference between those 5 orbitals. You put them in a different field. If you have something with 6 nearest neighbors, that's an octahedral field. That's the simplest way to understand it. If those neighbors are different, you might have like a C4V or some other kind of symmetry. But the 2 classic cases are the octahedral or the tetrahedral fields. What I mean by field, well, if you think about that central atom and its d-orbitals and you have 6 nearest neighbors, those interact with that electron cloud at those 6 major points. And so it generates a field that has octahedral shape. So that's a very important word in inorganic chemistry, the crystal field. So when you put this in a crystal, you have a crystal field. But if you just have an octahedral arrangement of nearest neighbors, you have an octahedral field or octahedral crystal field. And that causes a splitting of those d-orbitals. Now, what I'm discovering too is you have bonding and antibonding orbitals too. So it may be the 3 d-orbitals drop and 2 of them go up, or it might have the opposite effect. 2 drop and 3 go up, but it's always this 2 and 3 set. And we'll see why that makes sense when we look at the photos. In a tetrahedral field, many inorganic compounds, you see those 2 orbitals drop and the 3 orbitals go up. Which of those 3 orbitals that are similar to each other? Think about your d orbitals. You have the dxy, the dyz, and the dxz. Those are exactly the same orbital, just different planes. And so those always go together. Those 3 xy, xz, and yz orbitals go together. So whenever you see a splitting pattern like this, and you see 3 orbitals either high or low, you know those are the xz, yz, and xy d orbitals that have stayed together. The other 2 are that dz squared minus x squared minus y squared, and then the x squared minus y squared. So that's a pair of d orbitals that stay together. So let's dive into the pictures. This is the coordinate system that we're going to be using. So this is an octahedral complex, and I've shown the axes here. You see the x-axis is kind of coming down diagonal to the left, the y-axis diagonal to the right, and the z-axis is pointing straight up. And so all of the orbitals in this PowerPoint are based on this coordinate system. So when you see something coming out diagonally towards you, that's the x-axis. And so if you have a p orbital that's along that diagonal, that's the px orbital. And if you have one going down to your right, that's going to be the py orbital, and one going up and down is the pz. So let's look at the energies. These are the energies that came from Gaussian. Now this wasn't a very high accuracy calculation. It was the minimal basis set. So Slater type orbitals, STO, 3G, and that's just, I wanted to not have any confusion of it adding d orbitals and stuff and p orbitals to the hydrogens. I wanted just the minimal atomic orbitals that we know that we could write down by hand. And that's, if you ever want to do that, that's the STO3G basis set. And I did Hartree-Fock theory, so these energies may not be exactly accurate, okay, but they are sort of ranking them, and you can still learn some things from this, like the core electrons are way far down. So here are the energies. I've converted them to kilojoules per mole. I don't know if that was useful or not. The tetrahedral complex I left in Hartree's It's really just interesting to look at the relative magnitudes of those orbitals. So I know you probably can't see this writing, but it starts down here at the chromium 1s orbital and goes all the way up to the highest antibonding combination of the 4s and the hydrogen 1s's. So let's go through each one of these and look at the molecular orbital diagram. So this is the full molecular orbital diagram for this chromium hexahydride. Notice you have one little energy level down here at the bottom, and then you've got a stack of energy levels up there near the valence band. What do you think that lowest energy is? It's the 1s orbital, right? So then let's take this band up here and expand it. So let's take that energy region right there and just expand the graph. Okay, now we see the 2s and the 2p's on chromium. Still way down in energy to the bonding region, but you can kind of see the bonding region kind of expanded a little bit. Let's zoom in a little more. So now let's take all that area up there and expand it. Well, here we have the 3s and the 3p's, still not up near the bonding area. So this should drive home that that core electron cloud is just by itself in its atomic orbitals. So the chromium has the 1s orbital, the 2s, the 2p, the 3s, the 3p, all of those are down buried inside the electron cloud. They don't even know there's hydrogens out there. They're not bonding, they're not participating. So let's zoom in one more time and get this whole valence region on the chromium. And this is what we see. A little bit more complex. But we do see some things that are singly degenerate, doubly degenerate, triply degenerate. Those are your only three options. You have an s orbital that can bond. You have those z squared minus x squared minus y squared, and the d x squared minus y squared orbitals. That pair is the doubly degenerate pair. And then the triply degenerate pairs could be p orbitals, or it could be those d, xy, xz, and yz orbitals. And so we're going to go through and look at all the pictures of all these orbitals. But this would be the molecular orbital diagram. We fill in the electrons, we get up to here, and those are filled up to this point. You can also see that there's the zero in energy, so everything below here has electrons in it. These are the non-filled orbitals above zero. So let's go back, zoom out, and look at the pictures. The 1s, I went ahead and showed that molecular orbital, and it's so tiny, it's inside the ball. Okay, so you can't see it. Just the drawing of the molecule, the ball is bigger than the 1s orbital. Okay. Then we have the 2s, so we've zoomed in, and here's the 2s orbital. Now that 2s orbital is bigger than the little blue ball that was representing the chromium. And then we have the p orbitals. Look how tiny the p orbitals are in the 2s. They barely escape that blue ball that's the chromium in the middle. So why are they so small?
Because chromium is a lot more protons.
Right, let's look at chromium here. It's got 24 protons. Okay, so 24 protons pulling those electrons in. You know, it's Coulombic attraction. So those 2s orbitals are held so tightly close to that nucleus. So they're very, very small. Not even aware. Remember, these surfaces contain, I've got it set at 0.04. So that's 96% of that p orbital is held inside that surface. Okay, so that beyond that, that's only 4% of that molecular orbital is beyond that surface. And so those hydrogens are so far out, this orbital can't interact with the hydrogens. It's held too closely to the nucleus. Now we've zoomed in some more. Let's look at the 3s and the 3p's. So there's the 3s. It's getting close to the hydrogens, but still only a 4% chance of touching the hydrogens, less than 4%, because this surface contains 96% of the electron density. And so even the 3s is getting close to bonding with the hydrogen, but it's not there. It's not quite able to. And then here are the 3p's. So this is the 3pz orbital. Which one is this?
3px.
X, yeah. And this one's the Y. So you've remembered the coordinate system. That's good. Now in the octahedral character table, if you look at it, you'll see X, Y, and Z are the same. So that's the symmetry is T1U for the X, Y, and Z. The octahedral character table, that point group has an inversion center. So that means you have the G and the U. spherical objects in that character table are it's like x squared plus y squared plus z squared. That's the equation for a sphere. So the 1s orbitals are top row. So the s orbitals are top row. So that's A1G for the s orbitals, T1U for the x, y, and z of the px, py, and pz. So far, so good. These are mainly just atomic orbitals. Now it gets interesting. So this is the valence shell bonding region for this molecule. You see the electrons have been populated up to this level, and that's it. We're out of electrons. This is for a neutral. So chromium brought in its 6 electrons. You see it has 2 here, and then 4 d electrons. All 6 of those are available for bonding with the hydrogen. And hydrogen brings 1 apiece. You add all those electrons up, and this is where you get up to this point. So if you could see these labels, you see down here at the bottom, this is the 4s plus 6 1s's. So I've shrunk that nomenclature down. It would really be the 4s on the chromium plus hydrogen A 1s, hydrogen B 1s, hydrogen C 1s, D, E, F. So we'd have all of those. I just, for shorthand, wrote 6 H1s's because they're all in phase if there's a plus sign between those. So this is the s orbital, the 4s orbital on chromium, in phase with all of the hydrogen 1s orbitals. So we should see just a big ball, and we do. Okay. Now what about this node in the middle? Remember that these 3s, actually the 2s, the 3s, the 4s, all of those have radial nodes. And so the 4s ought to have 3 radial nodes, and it does. It has one really close to the nucleus, one pretty close to the nucleus, and then this one you can see it's bigger than that blue ball. So that's the 3rd node on the 4s. It's a radial node, but that's still the 4s orbital in phase with all of those hydrogen 1s orbitals. So that's bonding all around. And then let's look at the d orbitals, the x squared minus y squared, and the dx squared, 2z squared minus x squared minus y squared. So we've seen this. These look like d orbitals, and you have them in phase with the hydrogens. So this one is bonding with 4 of the hydrogens. Do you see how this terminology, one more time, let's look at it. This is the dx squared minus y squared. So this is the x-axis, and this is the y-axis.
And because they are subtracting, they're out of phase.
Yeah, they're out of phase, and the x-axis is x squared, so the positive and negative are the same color. And minus the y squared, and the y is squared, so the positive and negative, the y-axis are the same color. So, man, hopefully that'll finally sink in. If you've had trouble with that, let it sink in. The x squared minus y squared means the x-axis is the same color on both ends of the x-axis, and it's the different color from the y-axis.
The z is canceled out.
And the z is not used in this one. And it's used twice in the other one. So this one is the 2z squared. So z-axis is used twice in this one and 0 times in the other one. And then it's minus x squared and minus y squared. So the x squared and the y squared are the same sign. So this, so let me draw on this one. This is the z squared, and see how it's big. So that's the 2z squared part. And then it's opposite sign from the x squared and the y squared. So that's x squared and y squared. And since the x squared and y squared are the same sign, they're both negative, they're the same color all the way around. And now we stick on 4 hydrogens on that ring, and it becomes this shape where we're bonding with all 4 of the equatorial hydrogens. And then we're also, the Z part is bonding with the polar hydrogens, using terminology from organic, So, yes?
Why are those 2 d-orbitals like so much lower than the other 3?
I think just because it's this able to expand over the hydrogens. It's in phase with the hydrogens, and so there's a bigger box. And so it's more bonding.
So if it was just chromium alone, would they all be on the same line?
Yes, if it was just chromium alone, then the d orbitals, all 5 d orbitals would be the same.
Okay.
Now, if they had the same number of electrons in it, Gaussian can actually calculate the spin orbit coupling, and fiddles with the energies a little bit. Okay, but if you were to just let's say you calculated the d orbitals on an atom that didn't have any electrons in those d orbitals, it'd be 5 degenerate orbitals.
So would chromium's like stable state where you have like one in each d orbital and like one in the
Right.
4s?
One in the 4s, and then and a 5d. Yes, they should be the same energy. Yeah. So, any questions about this degenerate pair? Okay, let's move to the next one. Let's look at these. This next one I thought would be the dxy, dxz, and dyz, but it wasn't. It was the 4p orbitals interacting with the hydrogens. So this is still T1U for all three because it's px, py, and pz, and it's those 4p orbitals interacting with those hydrogens. So what's happened is really these two d orbitals have really been stabilized in energy and dropped down below the 4p's, and the 4p's when they bonded also dropped down below the 3d orbitals. So these should be straightforward. You see, this is the pz orbital over here. This is the px, and this is the py. So now let's look at the splitting of the d orbitals. You see those two. We've already looked at those pictures. That's not anything new. And these are EG. So if you look at the character table, you'll see that z squared minus y squared minus x squared, and that will be on an EG row with the x squared minus y squared. So you'll see that in the octahedral character table, and you'll see that's on an EG row. Can you also look at this orbital and see that it's Gerada, it's even, it's a +1 under inversion? Because if I were standing anywhere on this electron cloud and I go through the center of mass to the other side, it's the same color. Okay. This one is one of those orbitals. I know if you can't see that, can you guess it? Like if I didn't give you that, that's XZ, could you see that that's XZ?
Well, it's going on the x-axis.
Yeah, so here's the X right there, and here's the Z, and it's between those two axes. So you find those two axes that this orbital is in that plane. It's in that plane of the XZ axis. Okay, let's look at the next one. Which one is that? Don't cheat, just look at it and see if you can figure it out.
Up and down, and one to one.
Yeah, see the action of those orbitals is expanding in what plane? In the XY plane. If you can understand these, inorganic is going to be so much easier. So I think this, again, inorganic chemistry, all of chemistry is really the interactions of the electron cloud. And so the more you understand about the electronic structure around a metal atom, the more understandable inorganic chemistry is.
I can see how it'd be easy to mistake it for a X though instead.
Just an X?
No, like a ZX instead of a ZY. I could see how it'd be easily mistaken. Oh, XY, yeah.
Yeah, it's XY, yeah. But notice how it's very similar to the x squared minus y squared. It says rotated 45 degrees. Okay, you see that? It's very similar to this one, which is x squared minus y squared, and the dxy is kind of the same thing but rotated 45 degrees. So in some character tables, like maybe C4V or whatever, those will pair up. Okay, but right now we're just talking about octahedral versus tetrahedral. And then this one, that's which plane? The YZ plane. You see it? It's it's in this plane here. So the y-axis and the z-axis are involved, so that's the YZ plane. Okay, good. Okay, so then let's look at those antibonding orbitals. Notice over here on the energy slide, I'm color coding these. So these are the bonding ones. I have here that dz squared minus y squared minus x squared minus y squared plus 2 1s. So that's sort of in phase with 2 of the 1s's. Up here, it's out of phase with those. And so let's look at those. You see how it's out of phase with the 1s orbitals? So there's a node that breaks the bond. So we have the bonding down below and we have the antibonding up above. Just like we saw in diatomics, you know, you have the PZ orbitals come together and they can have a bonding and an antibonding arrangement where the antibonding has a node that cuts the bond where the bonding doesn't. Okay. What do you think this one's going to look like? Well, it's going to shrink and there's going to be different colored balls. So the hydrogens around the middle are going to be red colored and the hydrogens on the end are going to be blue colored or green. I don't know my colors. Yeah. Okay, it's swapped the z orbital. But still, you see that the hydrogens are different colors than the dz squared minus x squared minus y squared orbital. And so those would be, so that's that splitting, but for the bonding and the antibonding, it's split that much. Feeling a little more comfortable with these? Okay. Hopefully you'll be able to understand the d orbitals now.
So would that be the one that looks like it's like two pi bonds and then like a donut around it?
That's what this one is. It looks like a p orbital with a donut around it, but that donut now has these 4 hydrogens on it, and it's expanded to touch those 4 hydrogens. But if I were to take the hydrogens off, you would see that donut around the middle, and then the looks like a p orbital with a donut. Yeah. But it's just that donut now is spread around those hydrogens because it's in phase, and up there the donut is in the middle, and it's actually squished kind of like a square. It's like they packed the box too tight and the donuts are square. Ever happen that? Yeah. So it's just bumping into those 4 hydrogens, and now that little donut is a square shape. It's red. And then that what looked like a p-type character for the dz squared orbital is squished inside. And it's out of phase with all these hydrogens, so that's the antibonding arrangement.
And then the hydrogens will only fill up the p orbitals instead of the d because of like, is that like because light's like 1 unit of angular momentum, they can only go from like S to p?
We'll see. We'll do the selection rules for this one. Yeah. So we're going to have options where can it go from EG to EG or EG to T1U, and we'll do those next.
Okay.
Yeah. Now let's look at the 4p antibonding orbitals. So you might imagine if this is the py orbital, if I just change the color of that hydrogen on either end, then I'm going to have nodes that break those bonds as well. So up here you see the pz. So just like we drew in our molecular orbitals for the diatomics, for those pz bonds, you have nodes that break those bonds. The px and the py. Do those make sense to you? Can you see how the hydrogens have now swapped and they're out of phase with those p orbitals? When they're in phase, the p orbitals can expand to include the hydrogens. When they're out of phase, then there's a node that cuts that bond. And so those would be antibonding. And lastly, let's look at the dx. Let's look at the 4s ones. So that's the 4s in phase with all 6 hydrogens, and then you could be out of phase with all 6 hydrogens. It's the same symmetry, but one's antibonding, one's bonding.
So the center is out of phase from the rest.
Yeah, that radial node is it's just the radial node here for that 4s orbital. You could think of the radial nodes more as like a change in density of the electron cloud. So one portion away from the nucleus is getting more dense while the inside portion is getting less dense, and then the opposites happening. So it kind of hurts my head a little bit to think about, but you know, in the middle you've got a sphere that's expanding, but around there's a shell that's compressing. So kind of like sound waves coming out from the very center of the nucleus, if you think of it that way. But it's standing sound waves, and so there's a region where it's not really changing, but it's getting denser and less dense in between those nodes. And so then let's ask our D to D transitions allowed. We have this EG set of d orbitals and those T2G sets of orbitals up there. And can we make this transition? So this is familiar territory. You should be able to look at this and go, okay, I know these are, the symmetry here is EG, the symmetry up there is T2G. I look at the octahedral character table and I see X, Y, and Z, and that has the symmetry of what? Let's see if you were paying attention earlier. So the p orbitals were also X, Y, and Z. And so what were the p orbitals? What symmetry were the p orbitals?
T1U.
T1U, okay? And so that's all three things that I need. I have the upper orbital here, the T2G. That's where I'm going. The EG is where I am. I have electrons in that orbital. And then X, Y, Z polarized light would be T1U. The nice thing about octahedral and tetrahedral systems is you really just have one problem because they're kind of spherical if you think about them. They're the same from all directions. And so X, Y, or Z polarized light will behave the same in that system. So I don't have a specific one for Z and then one for X and one for Y. But yes.
Why did it decide to bond with the x squared minus y squared versus xy or xz, yz?
Okay, look at the pictures and you should be able to tell me that. Okay? Think about those XY, XZ, and YZ orbitals. They don't point at any atoms.
But couldn't they have just bonded there anyways, and then the other ones wouldn't be pointing at those atoms?
If they bonded, let's say they bonded to this middle one. The only one they really have an option to bond with would be let's say we rotated it 45 degrees and they bonded with this one, right? But we have to rotate that one 45 degrees, and this one would become that one, and that one would become this one.
All right.
Yeah, and so it sort of naturally falls into this 2 and 3 pattern. Yeah.
So it's always going to be the x bar.
It's gonna, yeah. And so these guys are gonna be aimed right at the atoms, and those others are gonna be aimed between the atoms.
Gotcha.
And the ones aimed at the atoms can bond, and the ones aimed between don't. So these came across really as non-bonding orbitals. If we were look at the atomic orbitals on chromium, we would see the 5d orbitals pretty close to the energy of these three, which are not participating in bonding. So this would be around the energy of all 5 of those d orbitals. And then when they came in and interacted with the hydrogens, 2 of them that were bonding dropped down here. And these stayed non-bonding. So they stayed where they were.
So those will always be non-bonding.
In the octahedral sense, yes.
Okay.
We'll see in the tetrahedral sense, it's weird.
Okay.
And then the Gaussian may be incorrect, and so I do put an asterisk on here in terms of the 4p's versus these. These may have electrons in them and just have non-bonding electron pairs in them. Okay, and so if my calculation is correct, these are lower in energy. But if Gaussian's not correct with this minimal basis set, then there might be a switch. Okay. So let's look at the selection rules for the D to D transitions. So this T1U times EG gives you this pair. So I think this was confusing a few people on the test last time. You look at the direct product table that I hand out, and you just see T1 and E. And so you see T1 times E gives T1 plus T2. But you also got to do the G and U symmetry. So you start with G and U's, you got to end with G's and U's as well. So you take U times G, and that's U, so then it's T1U plus T2U. So some people did the T1s and T2s, but they didn't do the U's. Okay. So you got to do it in 2 parts. You do the T1 times E, you get T1 plus T2. And you got U times G gives U. And so both of those are U. Now, we have this T2G times this whole set. So it's going to be T2G times T1U. And that's going to be these top 4 pieces here. Okay, so T2 times T1 gives A2, E, T1, and TU, T2. And then G times U is U, 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 U. Okay. And now T2 times T2 gives A1, E, T1, and T2. G times U is U, so everything's U. I've got an A1 here, but it's a U. And that's not top row. So that's equal to 0. Because I look in there, I don't see A1G anywhere. So even though I have all of these integrands added together, I have no top row. So all of those, when I integrate over all space, are going to be 0. So the D to D transition in an octahedral complex is not allowed. Okay. So how can octahedral complexes be strongly colored, which many of them are? The octahedral field is always slightly broken by vibrations. So it might go to a C4V if the top hydrogen vibrates up a little bit. Now you got a C4V, and you lose GU symmetry, and boom, it's allowed. Okay. So what that also means is that this octahedral nature should be temperature dependent. So if I cool things down and cancel out those asymmetric vibrations, then I might see the color bleach out. And that's an experiment I've always wanted to do, but haven't had the facilities to do it. So if you ever get a hold of a liquid helium cryostat and a visible spectrometer and some inorganic complexes, give me a call. We'll collaborate. Yes, exactly. And this is actually easy when you're looking at this. If I see GUG, if I see one U in a direct product system, I know just by GU symmetry this is not going to be allowed, because that one U spoils the soup.
If you have 2 U's, you might have G.
Yeah, if I have 2 U's, then the U's will cancel and I'll get G's in the end. Now I've also got to do all of the other parts of the direct product. But if I just see one U in there, then it's going to mess me up. If I see 3 U's, it's going to mess me up as well. So an odd number of U's will kill it. Okay. Let's look at the HOMO-LUMO. So this would be the p orbitals to the dx, y, xz, and yz. So is this one allowed? So we have T1U in the bottom, T2G in the top, and T1U for light. This one's even bigger because it's got 3 T's times each other. So it expands and expands and expands. So the first product gives us a set of 4 pieces. And then I have T2 times each one of those. And it gives me this huge thing. Okay. It's the same skill, but just expanded a little bit. So I've color coded it for you. So T2 times the A1 gives a T2. And G times G is G. Then T2 times E gives T1 plus T2. G times G is G. So that's both of these pieces here are the next one. And then T2 times T1 gives me this whole set. Why are these so big? Well, remember T stands for a 3-dimensional basis set. And so you've got something that's 3 times 3. We should see 9, right? And look at this. We see 3 here, 4, 5, 6. E is doubly degenerate, so 7, 8, 9. That's pretty cool. Okay, so it's all in there. Okay, if you know what the letters mean. And then T2 times T2 gives me this bottom one. And it's nice because we know anything times itself is going to contain A1. So T2 times T2 has an A1 in it. And it's G times G, so it stays Garada. So we have that A1G, which means this is non-zero. So we do have the HOMO-LUMO transition allowed in this metal complex. So the HOMO-LUMO is allowed. We can jump from that p orbital to these non-bonding dxy's. And we even see this in, that was sort of a covalently bonded situation with the hydrides, but we see this in coordination complexes. You put an ion in water, and water molecules snap on there in an octahedral complex. And so we have, here's just the same kind of pictures, but with a water molecule. And you could go find the molecular orbital of water that is being used here by this d-orbital. And so this is the d complex, or d-orbitals bonding or coordinating with water. Let's look at the tetrahedral complex. We'll go a little faster through this one. I didn't use Excel to make the MO diagram. This time I found a feature in Gaussian that allows you to put the energy levels that it calculates in an MO diagram. So up here in the top right is the MO diagram that Gaussian produces, and you can see the degeneracy and so on. The core atomic orbitals are unchanged, so you've already seen those. Let's go into the valence region and look at that. Here's the titanium 4s and the 4 hydrogen 1s is bonding. In this case, I've twisted a little bit. Now the x-axis is coming out to us, the y is to the right, and the z is to the top. And I'm looking at this orbital, and I'm thinking, what the heck is this? Right? That doesn't look like anything that I've seen before. Okay? And I had to stare at it a while, and then I realized what was going on. It's a p orbital in the z direction. You can kind of see that because it's red on top and green on the bottom. So that looks very much like a z thing. And what is the z? Is pz. What would you see if you saw something in the x direction? The px. What about the y? The py. But it's got this weird sort of interlocking nature, and that comes from the dxy orbital. So the dxy is mixing with the pz and giving us this interlocking shape. So I've shown that down here. I have the pz orbital mixing with the dxy. I just want to sit on this for a little bit. Look at those two bottom pictures and think about what would happen if I took this red expanding region on the top of my chromium and this pz orbital and mixed it with these two red pieces. It's going to cause them to get bigger, and they're going to go up, and then they mix with the hydrogen 1s orbitals. It's going to look like that shape.
So it would lower the green areas because the red and green cancel out, but expand the red because they'd add.
Yeah, and then sometime later it would change color and go the other direction. So it's causing, if you think about that dxy orbital, it's causing it to oscillate up and down according to those red and green regions. It's pulling the reds up and pulling the greens down. And you see, if I take this orbital here and I pull the reds up, they can bond with two hydrogens, and I push these greens down, they can bond with two hydrogens in the tetrahedral system. We a lot of times draw a tetrahedral system as if it's a pyramid sitting on three legs and a stem going straight up. But it's easier to think about a tetrahedral system if you draw it in a cube. Okay, so let's draw this in a box like this. Do you see the box? These are the front edges. Just think of a dice. And the hydrogens are on the opposite corners of the dice. Now can you see what we're doing here? And if you look at a dice, the X, Y, and Z axes are coming straight out of the faces of that dice. And so that dxy is right here, and the pz orbital is pushing the red parts up to bond with those hydrogens and the green parts down to bond with the other hydrogens. And we have three of those. We have three p orbitals, we have three xy, xz, and yz orbitals. And so we're going to have three orbitals that are the same energy, just like this. And so I have the 4px and the dyz. And so the dyz is this orbital. Here's the y-axis over here. Here's the z-axis over here. And the px is coming out to the front of us. And so it's pulling the reds forward and the greens back to bond with those hydrogens. Now, what hydrogens is it bonding with? It's bonding with two of the hydrogens, and I put out of phase with the other two, but since the orbital has plus and minus regions, it matches the plus and minuses on those hydrogens. That's really just showing that two of the hydrogens are out of phase with the other two hydrogens. And then here's the third one that might be a little easier to see. That's the xz orbital and the py paired together. And I have those for your benefit right here. So since I've built this PowerPoint, I'd like for you to go back and study it so that you can understand what orbitals mix to make these different pictures. All the subscripts are there for you to think about. So that's a triply degenerate pair, and that's the T2 pair. Also, that I've circled this. Notice that the X, Y, and Z are T2, and so are the XZ, YZ, and XY. Since they're the same symmetry, they can mix. That's another reason why they can mix. And so then we also have non-bonding, same kind of thing, but without the hydrogens. We have that PZ and the XY, and then you have the PY with the XZ, and then you have the PX with the YZ, all three degenerate. And then we have the X squared minus Y squared, not doing anything, because it's not aimed at any of the hydrogens. And then the DZ squared, 2Z squared minus X squared minus Y squared, not bonding with anything. So this is the opposite situation that we had at the octahedral. These are not pointing at any of the atoms, and so therefore they don't interact, and these come across as non-bonding orbitals. And then finally we have the 4s out of phase with the hydrogens, and then we have the anti-bonding of all of these three combinations. So this is the molecular orbital diagram. It's not quite as pretty as mine, if I say so myself, but all the symmetries are there, and we can do the selection rules. So can we go from the HOMO to LUMO? We have a T2 going to a T2. We don't have G's and U's. Now, I had a mistake on one of my character tables. I don't think it's the one I passed out to you guys, but it was a copy-paste error. I took the octahedral character table and turned it into the tetrahedral character table, and I didn't erase the G's and U's. So if you ever see a tetrahedral character table that has G's and U's on it, that's my mistake. You need to scratch out all those G's and U's. There is no inversion center in a tetrahedral molecule. It can't go to the other side. The hydrogen has nothing to invert into. So if you see on your character tables on the tetrahedral character table G's and U's, that's a mistake. Scratch them out. Okay. I found another one in my office yesterday. I was like, it's back. So, it's just like the plague. So T2 times T2 times T2. I mean, surely this is going to work out, right? And it does. So here's all of the different pieces. T2 times A1 times E times T1 and times T2. And we see that A1 buried in all of those. Once you find A1, top row, you're good. Not equal to 0, and the HOMO to LUMO is allowed. What about the D transitions? Now we have a T2 going to an E. So you just break those pieces out, and you have the E times A1, E times E, T1 and T2. And we have A1 from that second multiplication. E times E, you get A1. And so the D to D transitions are allowed. So the conclusions for this whole thing is that metal complexes have many allowed transitions, and so they form many colored compounds. And those d-orbitals are pretty high in energy, and the antibonding arrangements are pretty low in energy, so you have HOMO to LUMO transitions that are in the visible region. And so the earliest pigments were all metal-based. They had transition metal-based pigments, and so that's how you can tell in art if it's a forgery. You think this is some ancient painting, and you go in there and you find a polymer paint. They didn't have polymer paints back then. They had metal complexes, and you can see here, these are some pretty amazing things. This is chromium-3. This is chromate, dichromate, manganate, permanganate. Here's nickel, copper, cobalt, iron. I mean, you can get all the colors of the rainbow just from the second row of transition metals. And that's what makes inorganic chemistry so cool. If you look at some of Dr. Norman's crystals, they're absolutely fantastic. So anyway, that's a plug for his research. All right, well, I'll see y'all well, I won't see you next time. Next time I'm on a trip, but I will put a video lecture up. So be watching YouTube. I'll put a link also on Blackboard. So enjoy your rest on Friday morning, okay? And I'll get those exams back to you on Monday. Okay.
Also, you said my organic chemistry, everything is colored.